Imagine with me that it's the 1980s, and you have written a very important letter to your bank. It contains lots of crucial financial information, numbers that must be recorded in the absolute correct order. With your letter in hand, you leave the house and walk down the road to the nearest postbox. But instead of having it in a sealed envelope with the address of the bank on the front, with the name of your account manager Steve, and your home address on the back, you instead pull out a pair of scissors. And you proceed to cut your letter into tiny small squares, then throw that pile of paper confetti into the postbox. You would be insane to think that your letter would ever make it to Steve. And even if somehow, by some miracle of just random chance, some pieces of it made it to him, there is no chance Steve would ever be able to make a bit of sense out of it. Well, this is how the packet switching process we discussed last episode would work without these next crucial steps of the process of how we send data across the internet. In fact, there wouldn't be an internet, we would just have a chaotic stream of fragments of binary data being fired off without direction from a bunch of computers. No communication, just noise and chaos. Let's find out how it all works. In the early days of the ARPANET, which would evolve to become the internet we know and use today, there were other computer networks beginning to spring up in various places throughout the world. Only one of the biggest barriers to this becoming the shared global network we have now was finding a shared set of rules for how the computers would communicate with each other. Early on, many of the networks operated on different sets of rules or protocols for how data would be sent and translated. This was a little bit like an English speaker with no knowledge of other languages trying to read a page written in French, or vice versa. The same basic letters are there, but the rules governing their usage to convey information are completely different. Both networks were sending and receiving binary data, but the rules surrounding that data governing its transmission and translation needed to match. The set of protocols that the ARPANET eventually settled on, and that in turn were adopted by networks globally, came to be called TCP/IP, and they are still the same protocols that allow the internet to run today. Now, there is a lot of complexity we could go into here in explaining how this all works, but for the sake of time, we'll try to keep this fairly broad and easy to understand. We're not trying to train you to be network engineers after all, we're just looking to explore process and understand it better. But the first of the protocols we'll discuss is IP, or Internet Protocols. And if we call back to our opening story about your letter to your bank account manager Steve, at its simplest you could think of IP as the envelope with the address written on it that you should have put your letter in. Every device connected to a network has something called an IP address. This is a series of numbers that identify your unique device and its location. So when your computer wants to send some data over the internet to another computer, it wraps that data with some extra information called an IP packet. And within that IP packet, we'll find the IP address of your computer and the IP address of the receiving computer, much like an addressed envelope. This ensures that the network knows who the data is going to and who it came from. But the IP, or Internet Protocols, are even more than just rules around addresses. Incorporated within IP are the processes of routing and path determination. Firstly, let's talk about routing. The enormous network we call the internet is in part possible because of devices called routers, which are devices that allow the forming of networks and manage the data flow within that network and to and from other connected networks. You may recognize the term router from your home internet package. When you signed up, you would have received a router and a modem. In some cases, both are in the same device. The router, most likely a wireless router, is what creates your home network that your devices and computers connect to. But this isn't what connects you to the internet. You could use that router on its own to send data between your home network devices, but not beyond that home network. Conversely, you could also use just your modem to connect just one device to the internet. But in today's modern age, where we want multiple computers, phones, and televisions connected, that's not ideal. So in our multi-connection era, we need the router to create a home network, which then via the modem we can now connect that home network to the wider internet network. So data sent from your computer will first go to your home router. Then the packet will then be sent on via your home internet connection to pass through multiple other routers before it arrives at the destination computer, sometimes spanning the globe in fractions of a second. And at each router, the protocols we call IP will help decide which path that data takes. searching for the most efficient path, which is what we call path determination. You could almost think about routers like a distribution center in the mail network. Mail passes through, the address is read, and from there it is channeled into the next most efficient route. And if one route is blocked or congested, it will pick the next best one. If you ever want to see how many routers data passes through to access a given website, check out the traceroute function on your computer. It's fascinating. But what IP doesn't do is guarantee delivery, or check for errors in the data delivered, which when data is being split up into many tiny smaller packets seems like would be kind of important. So far, the IP layer has allowed us to put each piece of our chopped up letter in an individual addressed envelope to our account manager Steve. But there is nothing telling him what order those pieces are meant to go in, or if he hasn't received some pieces yet. One crucial piece could get lost and both he and I would never know. The only guarantee we have is that we're going to get a really angry phone call from Steve wondering why we chopped up our letter. And I feel like it's an illustration of how the internet works probably isn't gonna cut it as an excuse. But back to our story, we're still in a bit of a mess. Luckily, this mess can be tidied right up by using TCP, or Transmission Control Protocol. One of the most important functions of TCP is to ensure that all the packets your data is broken up into are able to be rearranged into the correct order. This works similar to if we had written a small number on the back of each piece of our letter after cutting it up, meaning that when Steve receives our incredibly annoying pile of mail, he will have some idea of what order each piece goes in and if any are missing. But thankfully, TCP means this process happens automatically for the receiver. It also follows a multi-step process to ensure the safe delivery of each packet of data. It first sends a small packet of data to the intended receiver as a connection request and awaits a response. If it receives a response called an ACK, short for acknowledgement, it will then send an ACK back, which is called the connection handshake. From there, it begins to send on the packets of data, but for each packet it is looking to receive an ACK in response. If it doesn't, it will attempt to send that packet again. Sometimes this will be just due to a delay as opposed to a send failure. In this case, TCP ensures the deletion of any multiples on the receiver end. When it has received an ACK for every packet of data, it will terminate the connection through a similar handshake process to how it began. TCP also has the incredible ability to either increase or decrease the rate that the packets are being sent at. It does this by measuring the amount of time for each ACK packet to return. If the time is very short, it will recognize potential available bandwidth and increase the data rate. If the ACK times begin to get longer, it will also recognize this and throttle back the rate the packets are sending at. Basically, you could think of this process like having tracked postage for each of your letters. But just like tracked postage, there is an extra cost. All those back and forward acknowledgements greatly increase the amount of data sending back and forward, therefore resulting in a slower speed of data transfer due to increased congestion. This is where other, less reliable, but faster transfer protocols, such as UDP, come into play, but we won't be getting into those for now. So we did it. Thanks to TCP IP, we can cut up our very important financial letter into tiny pieces and ensure each piece arrives with confirmation of delivery, and know that it will be able to be rearranged into the correct order. But we may need to find a new bank account manager, because no doubt Steve will be furious with us. Totally worth it though to explore one of the vital processes that make the internet possible. I can already feel the next question that may be rising in your mind though, and it's what does any of this have to do with how websites work? A big chunk of our time using the internet is spent on the World Wide Web. In fact, the web is so associated with the internet that we came to call accessing the World Wide Web going on the internet. But the web is a whole other entity with its own fascinating processes. So next episode, we'll get stuck into the web. Sorry, that was a terrible pun. See you next time.